Hey guys, in this lesson we're going to be studying titration, which will open up with a little discussion about neutralization and titration theory, and then I'll show you how to do the calculations. Your bookwork is here. It's questions 40 through 50 on page 185. And your aim today is, how can we find the concentration of an acid or base, assuming that you don't know it already? So I want you to follow that up with these do now questions. Of course, right here you can choose to do your own thing. You don't need to write all of that. Okay, neutralization is at the heart of any good titration. So neutralization is when acids mix with bases, but we can get more specific. For instance, what happens when 1 mole of hydroxide mixes with 1 mole of hydrogen? So since hydroxide and hydrogen combine to make H2O, or water, in a 1-to-1 ratio, then you can see that 1 mole of hydroxide with 1 mole of hydrogen really should just make 1 mole of water. But what happens if they're combined in a ratio that's not 1-to-1? What if there's 1 mole of hydroxide with 2 moles of hydrogen? So the 1 mole of the hydroxide would combine with 1 mole of the hydrogen, and you would get 1 mole of water. But I only used 1 mole of the hydrogen, and there's still 1 mole left. So you would also have a mole of hydrogen left. So this is a pretty important idea because it's showing that this is not a complete neutralization. We learned in this simple exercise that if you have more than enough hydrogen and the hydroxide runs out, then you will get some water, but you'll also have some ions that are characteristic of acids left over. So overall, that would be an acidic solution. Let's try another one with an opposite example. What happens when you have 2 moles of hydroxide mixed with 1 mole of hydrogen? So 1 mole of hydrogen will mix with 1 mole of hydroxide, leaving you with 1 mole of hydroxide left over, but also you'll get a mole of water. So I'll highlight that. And we have a mole of water and a mole of hydroxide left over, which means that the overall solution here is basic or alkaline. All right, now I'm going to show you a little bit of neutralization theory at the bottom of this page in this table. In the first scenario, we have 10 milliliters of 1 molar HCl, but we have 20 milliliters of 1 molar NaOH. So to figure out the moles of hydrogen we have in this substance, which is our acid, we're going to need to figure out, firstly, how many liters do I have? Because right now it's given in milliliters. And then secondly, once we know the number of liters, we'll use it in this equation here, which I rearranged so that it says moles is molarity times liters, but we will need those liters from the previous step. So this will be step 2. All right, so in step 1, 10 milliliters, divide that by 1,000 to get the number of liters, and you'll get 0.01. We need to multiply that by the molarity, which is 1 molar, and you get 0.01 moles. And for the next part, we need to do 20 milliliters into liters. So 20 milliliters divided by 1,000 gives us 0.02 liters. Multiply that by 1 molar of concentration, and you get 0.02 moles. So with this, you can see that you have more hydroxide than you have hydrogen, which overall means that we have a basic or alkaline solution. Let's go through this one again. In this case, we have 10 milliliters of 2 molar HNO2. So that means we have 10 divided by 1,000, or 0.01 liters of this acid. Its concentration is, of course, 2 molar. So that means we have 0.02 moles of hydrogen. And in the second scenario, we have 10 milliliters, or 0.01 liters. Multiply that by 1 molar, which is the concentration of the base, and you get 0.01 moles of hydroxide. So with 0.02 moles of hydrogen and 0.01 moles of hydroxide, you can see we have an excess of hydrogen, making this solution acidic. Last one on this page, we have 100 milliliters of 1 molar sulfuric acid. So 100 divided by 1,000 is 0.1, which is the number of liters of acid we have. The concentration of the acid is, in some senses, 1 molar. But this is tricky. Pay attention to this. I'll highlight it for you. There's 2 hydrogen atoms in every one of those formula units. So even though the concentration of the acid is 1, you do have 2 hydrogens for each of those. So I'm going to write down a concentration of 2 as the concentration of the acid, which means that 0.2 moles is how much hydrogen I have. Now for the next example, we have 200 milliliters of 1 molar LiOH. So 200 divided by 1,000 is 0.2 liters. The concentration of this base is 1 molar. And that means we have 0.2 moles of hydroxide. And when you compare the number of moles of hydrogen and hydroxide together, you'll see that they're the same. And that means that this solution would be of a neutral acidity or basicity. So on this slide, we're going to discuss titration theory. So titration is this process that we use to basically tell us what the concentration of an acid or a base is, even if we're not given that information. So a titration is a procedure used to determine the concentration of an unknown acid or base. So it'll be set up something like this, like it'll say you have a flask containing 100 mils of a solution of HCl of unknown concentration, and in a separate beaker you'll have an unlimited amount of 0.1 molar NaOH. So you've got your acid and your base. And then typically what we do is we add an indicator to the flask of acid. And this is like our flask of acid down here, who we don't know what its pH is. It has an indicator in it. If it's phenolphthalein, of course, at first it'll be colorless, because phenolphthalein is colorless in the presence of an acid. So you've got your acid and your phenolphthalein, it's colorless at first, but basically you're going to add the base through this tube. It'll drip down until it turns pink, like right now, or right now. So that would turn pink when it's in the presence of a base, meaning that you've neutralized all of your acid with base, and that basically the solution is neutral and you have no acid or no base left. It's just sort of in the middle, and we call that the end point. So the end point is when the solution is neutralized. Now when that end point is reached, you actually have no free hydrogen left because it's all been neutralized by hydroxide. And that would also mean that the ratio of hydrogen to hydroxide in that case would be 1:1. So all told, when the solution reaches the pink state, that's because you have gone from acidic into the territory of neutral, almost basic, and you have an equal number of moles of hydrogen and hydroxide at the end point here. Now the math that goes with this is basically relatively simple math. The way that we can figure out the number of moles of hydroxide that we used is by considering that the moles of hydroxide is really the molarity times the liters. That's what we did in the previous slide. So if you want the number of moles of hydroxide, multiply its molarity by the number of liters that you used. Same thing for the moles of hydrogen. And also, the moles of hydroxide are equal to the moles of hydrogen. So why not just do m times L equals m times L? And in that case, you'll get moles of hydroxide equals moles of hydrogen. And you can do some really simple math to get all of those answers. Now the setup for this titration has some specialized vocabulary, so let me go through that with you. A burette is, it's the large piece of glassware over to the right, and it's basically a volumetric dispensing column, and it is read sort of backwards or upside down or something. Basically, it's there to tell you from the top that you've used 0, and at the bottom that you've used, let's say 50. But it'll be numbered from the top to the bottom in increasing numbers. The Erlenmeyer flask is down here. It's a conical volumetric flask, and the stopcock is really just a valve, and the valve is helping us to open the burette and allow base to flow through. And then lastly, why is there an indicator in the flask containing acid? It's because the indicator will show us our endpoint, which we need to do our calculations. So as a review, here's why titration calculations work. If you have the molarity and the liters, you can find the number of moles. And if an acid has been neutralized, then the number of moles of hydroxide and hydrogen are equal. So if you can find out the number of moles of one of them, you can find out the number of moles of both. Or in other words, we'll just use M times L equals M times L. You can see more evidence of that here. Basically, M times L is the same thing as MAVA or MBVB, which is the way our reference table writes it. And it's basically saying that M times L equals M times L, or moles equals moles. That's what it is down there. And then here's an example of how to do one. The first thing you should do is read the question carefully. Make sure you have your bases, your base data separated from your acid data. And then you'll make a little table that organizes the information like I've done. Now from there, you need to figure out the equation to use and isolate the variable that you need. In this case, it's MA, or the molarity of the acid. So I'm going to divide by VA on both sides to get MA alone, and my newest equation looks like that. MA equals VB over VA. And then from there, of course, you can plug in the variables that you know, 0.25 times 50 over 20, and you can finally achieve your answer, which in this case is 0.625 molar for the concentration of the acid. So with that, we've reached our pair-up. Please copy down these questions before class and follow it with these summary questions, which we'll solve in class as well. Thanks for watching.